Okay, good afternoon to everyone. So, good afternoon. Today we will discuss on horn antenna. We have been discussing on radiation resistance and field due to circular loop and all those things. We have also seen the loop antenna, a general case. Today's class we will discuss upon the horn antenna, and we will see to that what is the properties of horn antenna and few equations about horn antenna. So this is what we know is the horn antenna is regarded as the flattered out or opened out waveguide. A waveguide is capable of radiating radiations into the open space. So what you can see is it is flared out and on an open out waveguide. So horn antenna is regarded as an flared out or opened out waveguide. A waveguide is capable of radiating the radiations in the open space. So in waveguide, a small portion of the incident wave is radiated. So what we are going to see here is in a waveguide, a small portion of the incident wave is radiated and large portion of the reflected is reflected back. So that is what it is happening. So a small portion of the incident wave is radiated and large portion is reflected back by the open circuit. So here, so you can see that I will show you the horn antenna, how it looks like. The small portion of the incident wave is radiated and the large portion is reflected back in the by the open circuit, and you can say that it is flared out. So antenna is regarded as the flared out or opened out waveguide. So here the open circuit is a discontinuity which matches the waveguide to space very poorly, and differentiation around diffraction around the edges will be provided by poor radiation or and non-destructive radiation pattern. So that is what it happens. The open circuit. So you can see that the horn antenna is a type of antenna where you can transmit the signals, and here the open circuit is a discontinuity which matches the waveguide to the space very poorly. Uh, so what it happens is you have the edges or the corners for any antenna. So it will lead to the diffraction around the edges, and as well as that's what you can see, the diffraction around the edges, as well as provides the poor radiation and non-destructive radiation pattern. So this is what you can see here. Uh, and the waveguide to the space is very poor, and this what it happens for the horn antenna. So to eliminate all these difficulties, the mouth of the horn antenna, or you can say that this is first I will show you the horn antenna. So this is how the horn antenna looks like. So you can see that this portion we call it as the mouth portion, or the portion where the signals are being transmitted to the outer space. So this portion you can see that to eliminate all these difficulties, the mouth of the waveguide is opened out, which assumes that the shape of the electromagnetic cone. If the waveguide is terminated by any type of cone, the obstruct discontinuity, that is called gradual transformation. Okay. So this is what it happens if the impedance matching, if you take, if the impedance matching is proper, all the energy incident on the forwarded direction and will now be radiated. So we can see that the impedance matching is, if the impedance matching is proper, the energy incident is forward direction will now be radiated, and you can see that there are two different types of horn antenna. Different types are there. We can see that it is sectorial H plane horn antenna, and this is an E plane horn antenna. So this is called as a waveguide, where you feed the signal, the input signal which comes which comes through this portion, and this is the portion we call it as a horn. So it is of the shape of a horn. That's why the name called the horn antenna has been explained. So this portion you have already studied before, the portion through which the radiation of the signal being transmitted as well as received. So that is called as the aperture. So we call it as the aperture. So if the following is done, if the flaring, so the process of flaring is there. If the flaring is done, so what you can see here, so when the signals are being transmitted or being received, no, what happens? The edges are there. So at the edges, the signals get lost, and all those things happen. So we have to minimize it. So you see, this sometimes we cannot eliminate the entirely, but we can minimize those things. So the flaring is done only in one direction, then it is called as sectoral horn. So if flaring is the process where you just make sure that the reflections or the edges where that losses are going to happen, that are eliminated to some extent. The direction, then it is called as sectoral horn. And flaring in the if in the electric and magnetic vectors, that is E and H plane. If you do the flaring in both the electric and magnetic vectors, or you can call it as in the E and H plane, it is done, it is called as the pyramidal horn. So then it is called as pyramidal horn. So you can see different types of horn antennas also available. So you have circular horn antenna, pyramidal horn antenna, sectorial H-plane horn antenna, E-plane horn antenna. So all those things are there. So this is the example for this is the diagram for pyramidal horn antenna, where you can see that the electric fields and magnetic fields are being transmitted as per the requirement. Okay. So the horn antenna can be of both rectangular as well as circular horn. So you, as I have told you, you can have both horn antenna as rectangular horn antenna as well as circular horn antenna. And this properties of this horn antenna is to have. So this is the shape of the antenna which you can see where the signals are being transmitted. So if it is H plane, it will look something like this, and this portion is called as the aperture through which the signals can be transmitted and received. You have studied in detail the apertures of antennas, and this is called as the E plane, where the signals it looks like this, in where the signals can be transmitted through the antenna. So here, so we have horn antennas can be both rectangular horn as well as circular horn. So that also we can see further. So this is another type of horn antenna. You can call it as a conical horn antenna. So in exams and all, we can ask you that what are the different types of horn antennas and all, and with its explanation. So this is called as a conical horn antenna. So the shape of the antenna is somewhere like a cone. So it is called as a conical horn antenna. So if the walls of the circular waveguide are flared out, a conical horn antenna can be obtained. So if you see that the circular waveguides are flared out, then the conical horn antenna is obtained, and you have seen now rectangular horn antenna, circular horn antenna, as well as conical horn antenna. So it's based on the application of the user. You can decide which horn antenna has to be selected, and you can rely on that those things. So the fields inside the waveguide. So when you take the fields inside the waveguide, it propagates in the same manner as the free space. But in the waveguide, the walls are concentrated by the walls of the waveguide. So the fields inside the waveguide propagate in the same manner as that of the free space, but the waveguide and the walls are concentrated by the walls of the waveguide, and on reaching the mouth means the end portion of that antenna. So on reaching the mouth, these propagating fields continue to propagate in the same general direction, but start spreading laterally. So that is what. So when on reaching to the final end of the antenna or the mouth of the antenna, the propagates in the same general direction but starts to spread laterally, and as the waveguide independent as the waveguide independence impedance. So if you consider the waveguide impedance and free space impedance, this does not match with each other, and so these are some of the properties you can say which the horn antenna will have, and uh, and which, if you take the direction at which the signal transmits, all those things can be considered. So as and when you take the waveguide impedance, the free space impedance does not match, and walls of the waveguide are flared out. So you can see that the walls means this portion. So this walls of the waveguide. So this is a conical shape. So the walls of the waveguide means this section. If you take the rectangular section, so this is a pyramidal horn, and you can also have circular as well as the rectangular horns as well. So all this horn antenna, you can see that the walls of the horn antenna are flared out, and the free space impedance does not match if the walls of the waveguide are flared out. So if you take the antenna such that the walls of the waveguide are flared out, means you can say that the free space impedance does not match with each other. So that is what you can see here. So the flared out structure is called as a horn antenna. So if you talk about the aperture, which we have studied in the previous module, the aperture is large and the directivity is high. So you have also seen the relationship of aperture as well as directivity in the previous module. So if you see that the aperture is large, if you think that you have a large aperture, then you can say that the directivity is also high, and this is flared out structure is called as the horn antenna. Okay, if you talk about the horn antenna, if that is the flared out structure is called as the horn antenna. So this is the we are going to see few equations in order to understand how these things can be measured. So the design equations of the horn antenna is what we are going to discuss further. So this is something theoretical concepts which you can understand about this horn antenna, and we have seen that the process of layering out, and we have also seen that the impedance matching as well as the free space impedance does not match if the walls of the waveguides are flared out. Okay. So and if you see with respect to the aperture and directivity of so if you take an antenna, if you take a horn antenna and you see that you calculate the aperture of the antenna and you see that the aperture of the antenna is large, then you can say that the directivity is also high. So you can have a very high directivity as well. So those things are there, and you have the design equation for the horn antenna, where you can see this is the diagram. So this is the portion where through which the signal enters into the antenna, and this is the mouth or plane of horn antenna, or mouth of the horn antenna, where through which the signal is being transmitted. So this is the portion. So the length of the antenna, that is L. So you can see that this is the length of the antenna, and you can also see that this small portion is delta. So the small portion where you call this is called as delta, and from this point to this point it is A. This is A, and the entire this angle is theta, and you can see that. So all this parameters we will use in order to calculate the equations for that. So you can see that as and when you see for this horn antenna, you can see that cos of theta by 2, when you write cos of theta by 2, you will get this in terms of L and delta. So you can see that this is entire thing is L, and if you say that this small portion here, it is delta. So when you write with respect to cos of theta by 2, you can say that it is L divided by L plus delta. Or if you take sine of theta by 2, you can say that it is A divided by, A is this entire portion, A divided by 2 into L plus delta. So you can just understand these things, and these were some of the some of those things which was related to horn antenna. So now you got cos of theta by 2 as well as sine of theta by 2. From these two equations, you know how to write the tan theta by 2. So tan theta by 2, here it will be A divided by 2L. So we have the entire length of the antenna as L, and theta is this angle, and so we are taking it theta by 2 to get the half portion of that, where you can write it as L divided by L plus delta, which is cos of theta by 2, and sine of theta by 2 is A divided by 2 into L plus delta. Now we have tan theta by 2 as when we have cos and sine, we can write for tan theta by 2, that is A divided by 2L. So theta is the flare angle. So this is the flare angle, and A is aperture, L is the length of the horn antenna, and delta is the path length difference. So you can see that the path length difference. So when you take here the small portion that is called as a path length difference, that can be obtained, that is delta. So so this here, this side will be L plus delta, and this portion will be L, and this portion is the aperture A, and so when you take a triangle, so you can see by taking a triangle OBC. So let us take a triangle OBC and try to find out that. So when you take a triangle OBC, so this is O, and this is B, and this is C. So this triangle I am going to take. So let us take this triangle OBC. So what you can write from that, L plus delta square. So you take L plus delta square, can be written as, see the triangle, L plus delta whole square can be written as L square plus A divided by 2 whole square. So you can see that triangle L plus delta whole square can be written as L square plus A divided by 2 whole square. So from this, when we simplify it further, since delta is very much less compared to L, I have told you delta is the path length difference, so it is going to be very small, and when delta is very small compared to L, so you can simplify this equation further. I am just taking L plus delta square. So L square plus delta plus 2L delta is equal to L square plus A by 2 whole square. Since the delta is very small compared to that of L, you can just say that L from this some few terms get cancelled, L square get cancelled, and since delta is very small compared to L, and when you see that, so this can be eliminated. So what it is left out, it will be left out that 2L delta is equal to A square divided by 4, or you can calculate the L. So what you can do here is you can calculate the L. L is, what is L? L is the length of the horn antenna. So that theory portions and all, you can make a note of it from this diagram. You can just write down these equations and you can proceed further. So you can make a note of that diagram and those equations. So draw that diagram, and that theory portion I have already sent you. From that you can note down those things. You can make a note of this diagram and few equations. So you can note down these equations. Have you drawn this diagram? You draw this diagram, and you can make a note of these things in later stages. You can just note down these things about horn antenna. Just give a title horn antenna. This portion I have already, it's there with you. You can make a note of these things. Now you can directly go to the this diagram and you can make a note of these equations. So when you see here, have you drawn this diagram and these equations? Have you completed this? Harshita,
Yes, sir.
shall we move further?
Yes, sir.
Okay. So you can just make a note of it. Triangle OBC you take. When you take triangle OBC, you will get it as L plus delta whole square is equal to L square plus A divided by 2 whole square. So simplify that. When you simplify that, you will get 2L delta, since delta is taken as very much less compared to that of the length of the antenna L. So since you take it like that, you will get 2L delta is equal to A square divided by 4, and you get L is equal to, you will get L is equal to A square divided by 8 delta. So you get it like that. L is equal to a square divided by 8 delta. Now we also know that tan theta by 2 is a by 2l. So from that I can just write theta. Theta can be written as 2 tan inverse of a by l, or I can also write as theta can be 2 cos inverse of l divided by l plus delta. So this is the equation for theta. Theta is called as a flare angle. So you can make a note of these things. So this is the flare angle theta, that is 2 tan inverse of a by 2l, or it can also be represented as 2 cos inverse of l divided by l plus delta. So theta is the flare angle, and so we got this equation for L. L is the length of the horn antenna. We got the equation for L and theta. So you can note down these things. Have you completed? Is that over? So you can make a note of these equations. Is that over?
Yes, sir.
Okay. So we got theta here. Now we will continue with that. So half power beam width of optimum flared horn is given as phi of E, and you can say that the phi of E can be represented as 56 lambda divided by AE, and phi H can be represented as 67 lambda divided by AH. So what is AE is aperture? AE is the aperture in the E plane, and AH is the aperture in the H plane. So this is the half power beam width of optimal flared horn. We get it as theta phi E and phi H, 56 lambda by AE and 67 lambda by AH. So which is with respect to the aperture. A is the E plane aperture and AH is the H plane aperture. From this we can also write the directivity equation. So the directivity equation for an horn antenna you can find by using this equation. D is equal to 7.5 AP divided by lambda square. So you'll get it as directivity is 7.5 AP. AP is the aperture, AP divided by lambda square, and power gain. Power gain can be given as GP. GP is 4.5 A divided by lambda square. So you'll get directivity as 7.5 AP divided by lambda square, and power gain GP is equal to 4.5 A divided by lambda square. So the applications they are used. So what is the application of a horn antenna is they are used for used at microwave frequency, and where moderate gain are sufficient. So what is the what you can say is they are used in a microwave frequency where the moderate gains are sufficient, and they are used as feed elements. Okay, so they are also used as feed elements. So you can say that the application is that they are used at microwave frequency where the moderate gain are sufficient, so where you can have a moderate gain, and they are also used as a feed element in this case. So these are some of the applications. So you can make a note of these things. That is all about the horn antenna. Now we will discuss about few different types of antennas, and so like we have some few different types of antennas like helical antenna, Yagi antenna, and parabolic antenna. So that will be the end of this module. We are almost close to that, 1 or 2 classes we'll wind up this module. So we can see that, so these are the applications of horn antenna. So you can make a note of these things. So you can make a note of these things, and then we will proceed with the different types of antennas, where we will be studying helical antenna. And helical antenna is very important. We'll be discussing on that. And so first you can complete these things. So, so this is all about the directivity, power gain, and applications of the horn antenna. Is that completed? You can just write down these equations as well, phi of E and phi of H. Is that over?
Yes, sir.
Okay, so that is all about horn antenna. You can also add a few more things like different types of horn antenna. You can just refer and you can add those things, various types of antenna, horn antenna, and you can just draw those figures for that. So you can just as a continuation of this, you can also write different types of antennas, horn antenna, and you can draw those figures and its shapes like rectangular horn, circular horn, conical horn. There are many. So you can write some around 6 to 7 horn antennas. Okay. So that is all about horn antenna. The last topic which we are going to discuss here is the types of antenna. So different types of antenna is what we are going to see here. So you can just write down types of antenna. First one is helical antenna, which we will discuss now. So the helical antenna, you can write down types of antenna, and the first one is helical geometry. So today we will be completing this 5th module. We have one more class today. So helical geometry. Here helical antenna. You seen the helical antenna? It's like you take one. If you take a wire, and if you just rotate it on a pencil or a pen, you can see that it will be having windings. Okay, you can see that it will be something like this. It will be having the windings like this. So that type of antenna is called as the helical antenna. So if you just take a wire and you just rotate it on a pencil or a pen, you can say that, or on any surface as per your requirement. So you can see that you will get a helical shape, or you can say that it looks something like a spring. Okay, it will look like something like a spring when you do that process of rotation for the wire, a piece of wire you take it. So as per your requirement, you can design a helical antenna, and that antenna should be capable enough to receive the signal as well as transmit the signal. So some applications you may have to go for more number of turns, or some applications you have to increase the length, increase the diameter of the wire, everything. So you can say that this is the helical antenna. You can just make a note of this thing. This I'll be discussing with precise points. You have to enlarge these things, and you have to prepare answer for that. So you have to prepare the notes for this types of antenna which I had sent you already. You can make use of that, and you can prepare the notes for this one. So helical antenna, this it is very brief in that. So you have to make the points and note down those things. I have shared you almost 20 to 25 page notes. Okay, so that you can utilize it for understanding these things. So helical geometry is what I was saying. It is something like a spring, or where you rotate a wire on top of a pencil or a pen, or you get that entire shape of a helical antenna. That is called helix. Okay, so this axis is called as the helix axis. And this from here to here, you have the D, and this is the diameter D, and the entire length, this one rotation, you can say that it is L. So the spacing between one rotation to another, you can say that that is A, and the entire process, it is capital A. And this one rotation to another, you can see that that spacing is S. So these things are required for us to understand. So let me move on further. So as I have discussed with you, you can draw that figure. You write down helical antenna, and you can just draw this figure. I have given a detailed description in your notes, which you can take it. Okay, in WhatsApp I have sent you that. So you can just draw this figure. You can write down helical antenna, types of antenna. Okay, in that one is helical antenna, helical geometry. So you can make a note of these things. You can draw this figure. So this length, the diameter of the wire, and all those things are important for us to understand. So we can see that these are the parameter. D is diameter of helix, and or you can say center to center, and C is the circumference of the helix, which you can find by using pi d, equation pi d. C is the circumference of that, and S is the spacing between the turns, which I have told you. So one turn to another turn, what is the spacing? So that is S here, the spacing between the turns. And you have L. So L is the length of one turn. Alpha is the pitch angle, and it can be used by using S by pi d and all. N is the number of turns. So you may have 5 turns, you may have 10 turns or 100 turns. Based on your requirement, you can have the number of turns. So N denotes the number of turns. A is the axial length, and it can also be written as N into S. because n is the number of turns and s is the spacing. So axial length you will get it as n into s. D is the diameter of the helical coordinate conductor. So D is the diameter of the helical conductor. So you have diameter capital D and small d is diameter of the helical conductor, as I have discussed with you before. So you can make a note of these things as well. So few equations we will be seeing here, how to calculate some of the parameters and all you can see here. So as I have already mentioned that the diameter D and the circumference C refers to the imaginary cylinder whose surface passes through the center line. You have already seen that axis, helical axis. So this is the center line, helical axis. Okay. So which passes through the center line of helical conductor, and the subscript lambda signifies that the dimension is measured in free space wavelength. And for example, lambda, if you take d lambda is the helical diameter in free space wavelength. And if one turn, means I am saying that you can say that there are n number of turns, but if I am just saying that if I take one turn of the circular helix is unrolled on a flat plane, so you are just taking one turn and you are unrolling, that means you are just getting it back and just keeping on the flat plane. The relation between the spacing, that is the spacing is s and the circumference c, turn length is l, and the pitch angle will be alpha, which is illustrated in that figure, and you can see those things. And the dimensions of the helix are represented by diameter spacing chart, and which can be for the circumference spacing chart as well. So these things you can see, which we have already discussed. And on this the dimension of the helix may be expressed either in rectangular coordinates by spacing s lambda and circumference is c lambda, or in polar coordinates by the length of one turn, that is L lambda, and the pitch angle is alpha. So when the spacing is zero, so it's really difficult to have a zero spacing, but let us take that if the spacing is zero, then alpha is equal to zero and the helix become a loop. On the other hand, when the diameter is 0, so if diameter you take it as 0, alpha is equal to 90 degree and the helix become a linear conductor. So these are some of the cases when the alpha value is 0, the helix become a loop, and when alpha is 90 degree, you can say that it becomes a linear conductor. So you can just make a note of these things, these points. So you can have some mathematical equations as well for helical antenna, and you have to, so it's a it is very easy to do it, and only thing is that you have to have a uniform spacing. When you connect, connect it you can see that you will find that the signal can be transmitted as well as received. So are you able to see the it is available? It you can see, no, the slide. Are you able to see the slide?
No, sir.
Okay. Yeah, I will just take it there. No, just now it went, right?
Yes, sir.
Yeah. So you can note down those things, and we will in the upcoming class. So we will. This is what you have just understood, that how the shape of the antenna is, and what each parameter is in importance of that, and all those things. And if the spacing is 0, you know that alpha is equal to 0. Then you can say that helix becomes a loop, and if alpha is 90 degree, then you can say that helix becomes a linear conductor. So we will wind up with this here, and we will continue from here on in the next class. So that's all for today. Thank you.